Hey, yeah, welcome to discussion 5, slightly later than usual, but yeah, today we'll be talking about RISC-V instructions and call, or instructions encoding and call rather. But yeah, really quick, just as like to get a temperature check on people, is there any particular topic like out of, I guess, gosh, navigating back and forth isn't yeah, out of I guess calling convention like slash using the stacks with more general RISC-V stuff versus instruction breakdown versus call, is there any particular topic that like is more preferred, I guess? Or I'm asking online too. Yeah, I'm trying to like get this to spotlight correctly so we don't get like, oh gosh. But yeah, as we're doing this, yeah, is there any topic? Yeah, if there's not, then I'll just kind of go in the order that I think is reasonable. Oh my gosh.
Yeah.
Sorry, bear with me. I don't understand. How do I get you to spotlight? Hello. I'm not entirely sure how this is gonna work because normally oh, I can't spotlight on my own device, I think. Wait, Sydney, if I give you co-host permissions, can you spotlight it? Because otherwise you can't really see other stuff that's going on. But
Yeah.
okay. Okay, cool. And then can you spotlight my video? If you click on the 3 dots on the right hand side, and then there should be make spotlight. Okay, yeah, that looks right. Cool. So we're just gonna casually move this out of the way. Okay, great. Yeah. So I guess since no one seems to have a strong preference over anything, how do people feel about calling convention? I guess in person thumbs, and then online if you want to give thumbs as well. How are people feeling? Good, meh, not great about it? Right. Got one meh. How about in person? Okay, okay. Might spend like a minute or two going over it. Okay, slightly longer than a minute or two, but we're gonna then jump into like other stuff after that then. And then I'll be around for a while afterwards if you want to go over any questions. Okay, so yeah, just real quick going through this set of things. I think there's going to be a calling convention guide for project 2 that's going to be released today. I'm still going through it. But basically it's just a set of kind of rules that everyone who programs in assembly kind of follows to make sure that no one does anything funky. And so, well, the whole idea behind it is like you can use certain registers for certain things. Oh, also, by the way, the slides I posted online. So if you want to annotate on those, they exist there. But yeah, so like, why can't you use whatever registers for whatever you want? And the short answer is, well, you can, but it also means that you could possibly violate calling convention as well as just the naming conventions of what the registers are used for. So for example, you can use the RA register for literally anything in the world, but we've just said, oh, this is where we're designating the return address because there's usually going to be just one from a function. When you get into like parallel computing and stuff, that kind of stuff goes out the window, but we don't worry about that in 61C, which is great. Yeah, so you can, and there's no one really stopping you except for probably other annoyed programmers who are like, why are you using RA for like 0? But in reality, unexpected things might happen. You might run into this when you're running your 2B code eventually. 2A most likely won't have calling convention issues, but 2B is where you'll run into a large part of it, and it might be because you didn't follow it in 2A. So the idea behind it is, well, like this is like a way of communication between different programmers saying, oh, I'll make sure that certain things don't happen in my code. So for example, certain registers, even if they get changed in a function that I write, if you use it, you can be guaranteed that certain registers will return to you unharmed, the values, but certain registers won't. So then the answer is, well, or the question becomes, well, if I'm the one doing all the coding and I don't rely on any external libraries or anyone else's code, does that mean I don't have to follow it? And well, assuming that everything works perfectly, sure, that could work. Like you could just not follow it and it might be fine. But the bigger question is, do you actually remember everything you write? So how many times have you gone back like 3 days ago, like I wrote this code and now I don't know what it does? I have done that, yes. Especially, and when you look at assembly code, when everything basically looks like spaghetti, it becomes even more of an issue. So you probably don't want to go through every function that you're going to use just to make sure certain registers are changed. And you also have to worry about malicious users. So you can think of the 61C like Project 2 auto graders almost as like malicious user who will try to basically randomize everything that it can. And it's up to you as the programmer to make sure that the registers you want are saved properly and the registers that you don't want, they can be randomized in whatever form. So that might be why, like, if you're running the auto grader, you're like, I didn't change this like particular register. Why is the value different? The reason is because like you can't assume anything. There might be randomization that happens. There might be quote unquote other programs that are running that are setting those. So, and then the last part is, what if you want to make your code portable? So theoretically, you're like, oh, I want to like give my code to a friend. They should be able to use it without any issue. Don't do that on the projects. But theoretically, if you were to work on something and you're like, oh, my friend also needs to use something that I wrote, they should be able to use it with just the spec, so like basically what the function does and the parameters, so arguments and return values, without having to look at the code. Okay, are there any questions so far? Okay, so no, really quickly go through this. So yeah, calling convention makes sure that things can be in a black box, which just means that you can't really look into it. All you know are its descriptors, aka what it does, and arguments and return values, and you theoretically shouldn't need to know anything else about the function in order to actually use it. And so these calling convention usually exists in the span of like when you are using labels, because most of the time, theoretically, if you don't use any other functions and it's just like one thing through and through, it's highly unlikely that it'll actually come into play. But when your function starts being called, or if you start calling other functions, that's when it becomes an issue. But you have to make sure that you're using it in the correct places, because there will also be labels that look like functions, but they're actually loop labels, or for example, branching labels. And those, like, you can think of them as, like, for example, in a for loop, you go through things until you hit a certain parameter, and then you want to like return to the top of the loop. And so that's what that label is serving to do. But you know, like that's not an actual function call. So those don't have to follow calling convention. And branch labels, like for example, like branch if not equal between two registers, that's just an if else statement, and that's not a new function call. So you also don't quote unquote have to follow calling convention then. So it's only when you have function labels. Are there any questions? Yeah, these will all be available afterwards as well. So if you miss something, totally, it'll be okay. Okay, so we're just going to quickly go through the general rules for the caller and callee. So as a reminder, the caller is the outside function. So it's the function that's calling a different function. And then the callee is the function that's being called. So for example, if A calls B, A is the caller and B is the callee. Something to remember is all functions you should assume can be both caller and callee. So the kind of all functions are going to be designated as a caller, or sorry, a callee, aka something else might call it in the future, and you don't necessarily know if it's going to be or not. A function is a caller if at some point you use a jump or jowl or something like that inside the code. So for the caller, aka function A, you want to have a prologue, which happens before you call the function, and it's in quotation marks because we don't usually describe it as a prologue. It's more so just stuff that you do to set up the registers that might change across the course of a function call before you actually call the function. So you want to determine what volatile registers whose values you depend on after we complete the function call. So these include things like A registers, T registers, and the RA register. And these are considered to be volatile or non-preserved because they might be changed across whatever function that you're calling, and you can't be guaranteed that they'll be restored. So whatever comes out afterwards, you always have to reset that particular register before you start using it. Otherwise, the calling convention checker will yell at you. And then what you want to do after that is you want to allocate enough space on the stack by moving the pointer, aka SP, down by 4 times however many registers you're trying to save. So the reason it's 4 is because we have 32-bit registers and these go by bytes. And in the whole moving the stack down part, it's allocating more space because we start from a higher position, and to allocate space, you bring it down. So the memory addresses go, or the memory address goes down, so you subtract. Then you want to save the register values onto the stack. So you'll always use save word for this one. So not save byte or save half, or sorry, store half or store word or store byte, sorry, because you want to save all 32 bits onto the stack. And then so that kind of concludes what you do before you do the function call. So in between this one and then the next chunk, you'll do like JAL label name, and then or JAL RA label name, most likely. And then it comes to epilogue, or quote unquote epilogue. So this is what happens after the function is called, after you, for example, save whatever return values that you have into saved registers. Now you want to restore things. So the first thing that you want to do is you want to save the return value from the functions called somewhere else that you're not going to be using. So we know that return values come or are stored in A0, A1, and those are quote unquote volatile registers. So you might actually want to restore A0 and A1 to the values they were before you call the functions. But if you do that immediately, then you're going to overwrite the return values. So the reasonable thing to do here is to save those first, aka onto probably not the stack, but into a saved register first, before doing anything else. And then you want to load the register values into the appropriate registers from off the stack, so using load word. And this is just the kind of opposite of what you did before in the same order. And then you want to restore the stack to the original position by using plus, so add a positive of whatever you did before. Oh, I realized I didn't really kind of fourth one, but the fourth one is just basically like make sure that you have all the registers and that the stack like is where it is originally, because you don't actually know the value inside SP and you're not supposed to set it directly. All you can do is manipulate it relative to where it is currently. So to kind of make sure that quote unquote it's where you expect it, you want to just make sure every time you move the stack pointer down for something, you want to make sure that once you're done with the stack, you move it up the same amount. Are there any questions so far?
Where are
Yes.
the slides posted?
Oh yeah, the slides are posted in the central resources post. So I think the first, so the bottom pin post, a little bit down under the discussion tab. And yeah, all resources will be posted there before section, and then the notes, if we write anything, will be posted after. Okay, so the call, yeah, I'm gonna go through this a little bit quicker because so the caller is something that often gets forgotten. So these are, as a reminder, associated with the A, T registers and then the RA. This is often forgotten, and this is often the source of a lot of problems. The callee is usually easier to remember because you do it at the beginning of every function and at the end of each function. Whereas for the caller one, it only happens when you're calling a function. So similar to like what you have before, you shift the stack pointer down by the number of bytes you need. This is at the very beginning of the code before you do literally anything else. And you want to determine how many registers that you actually need. How many saved registers you need before you actually move things down, because you could save theoretically all the saved registers, but that's usually just poor practice because you use up more stack than you need, and it gets really confusing for you later on, like, oh, which registers did I actually use? So if you find that you're like, oh, I've run out of registers, then what you can do is basically just, okay, well, I'm going to go back and adjust it by bumping the stack 4 more down. So you just change the value to -4 more, and then save an additional register onto the stack. So if you find that you need more, you can always change it. So it's 4 times the number of registers. The negative value of that, you want to save the callee saved registers, aka the S registers, basically, and only the ones that you can anticipate overwriting later. So step 3 is kind of optional. So you remember earlier when we talked about RA, saving it onto the stack during the caller side. Oftentimes you'll see like sample code saving RA during the prologue and during the callee section. And the reason for that is just because it's like anticipatorily kind of saving the RA in case you call another function later on. If you don't call another function inside the rest of your code, you don't need that. But if you do, it's just a good place to put it to make sure you're keeping track of things. And then the epilogue, it's basically the opposite. You load it off of the stack, shift the stack pointer back, and you're pretty much done. So all in all, it's not too many steps, but it's just something you want to keep in mind whenever you're programming. Are there any questions on this whole section? Okay, cool. In the interest of time, I'm going to skip over some of the next few sections, but I can come back to it if we have time later on. Real quick question, would people prefer to go over a call first or RISC-V instruction format? Call, got one, yes, okay. Yes, got agreement for online, cool. Yeah, call is one of those topics that's like, it's like a big whoa question, so, okay. So, okay, as a general overview, I realize I can see my slides here, so I don't have to keep looking behind me, so I'll just pop it up here. The whole concept stands for, is an acronym for the process by which you get a C file or a low level file into some kind of executable that you can eventually execute. And the difference between the kind of like call and I guess like what you might be used to, like for example, when you're writing Python and Java, is the whole idea of like compilation versus translation. So what happens is when you're compiling things, you go through this entire process because it's very system specific, whereas with interpretation, because it's like within a certain environment, like the Python environment or the Java environment, it doesn't have to be system specific and can be run on interpreters. So the call kind of process goes from compilation using the compiler to assembling the code using the assembler, linking the code with a linker, and then loading the code with a loader. So the two sides are very like matchy. Before we get into all of that, we're going to talk about the C preprocessor. So Nick talked a little bit about this in lecture like ages ago, I think during the C section for about like 2 minutes total. But at that point it might have not made sense because you hadn't really experienced C code, nor had you like kind of thought about what it actually might mean. So if you look at the diagram from up top, the first process is actually going from some source C code into an intermediate file called CPP. So you might think of this as like CPP C++. It's actually the C preprocessor kind of like file that gets produced after preprocessing things. And what eventually happens here is basically like all of the things that like are preceded by a pound sign or the hashtag symbol without a space after it. Those things get expanded, which basically means the values get substituted for what they actually are, because the pound signs are just shorthand for preprocessor copy paste something else from somewhere else in your code into this particular section. And I don't want to physically see it when I'm in my C file, but to make sure the rest of it works, we want to make sure it's substituted in. So after that process, you get a .i or .ii file, and those are just intermediate files. It's actually pretty interesting if you want to look through like the GCC kind of whole compiler schema. Like you can have different flags to compile each of these. If I have time, I can like pull up a couple, and it's really cool to look at like how things are substituted in. But after that, what we have is then we go through the compiler. The compiler using GCC, G++ for C++, GCC for the GNU C compiler. And then what you end up with is a .s file. And .s files are just assembly code. More often than not, if you try to compile C code from scratch on your systems, it will most likely turn out to be x86 code, which looks actually slightly different from RISC code. But they're pretty much like the same in concept. It's just x86 is a lot more complicated and gross looking and fat. And then so after the kind of assembly code gets spat out, then you want to assemble it using the assembler. And so what eventually gets dumped out at the next step. So at the assembly code stage, you could theoretically still like look through and figure out what's going on, even though it's a little nastier. It's just kind of like going through line by line. After going through the assembler, you will most likely not be able to understand what the code does. If you do, you should go talk to some of the CS people. They will want to probe your brain. But basically the machine code is at the point where the machine can understand things with weird symbols and just like bits, but you as a human will no longer be able to. And so this is the step where all of the various different things kind of come into play. And then so after the next step, once you get the .o file, which is an object file, which we'll talk more about later, Then you take a bunch of different object files for whatever you need, kind of smush them all together. The linker smushes it all together, and then you eventually spit out an executable. So we'll go through each of these steps on this subsequent slide. But first of all, the preprocessor, just to go through it again, you might have seen like define statements. These are usually used for like constants, or maybe if you're a little failing PNC, some kind of like short functions. So these are just kind of like global things that you can reference later on in the code. And what happens eventually is you use like hashtag define, like it's usually in all caps. So like say pi is 3.1415. Then if you use the pi afterwards, basically what happens is you take the value and copy paste it into every instance of the code that uses pi. So the define statements, that data eventually sits in code memory because of that. And then you also have include statements. So this is something that you've definitely seen before. These are basically all the quote unquote imports that you have. So it might be like in Java, you have an import, I think in Python as well. And these basically, they're slightly different because what happens here is instead of like keeping things in a separate file, eventually after the Hi, did someone say something? Okay. I think it was just a random unmuting there. That gave me a little bit of a heart. But basically the include functions, you take whatever's in those header files and copy paste it into where the included in the code. And so after the preprocessor stage, like things will get expanded by a lot. Conditional statements, so pound or hashtag if, end if def, etc. else. So all of these directive statement or preprocessor directives modify how the code actually looks. In other words, after compilation, certain chunks of your code might not exist. For example, if like something isn't set, if you have it between an if and end if, that chunk might not exist if certain things aren't particularly set. You don't have to worry about it too much, but it's just something pretty cool that might show up. So these are all considered to be macros, and then the output here is a pure C file. Are there any questions? Okay, if you're like, oh, I don't understand how preprocessor work, that's totally okay. You're not required to for this class. This is more so like an overview of things. Okay, so now getting into the actual juicy thing. So we have our compiler compilation process. Oftentimes you'll be like, oh yeah, compile your C file into an executable. That is actually incorrect because the compilation is only going from the C file to RISC-V or some other assembly language, not an executable. So it's often like a misnomer in that sense. And it doesn't happen for high-level languages, aka Java, Python. What other high-level languages are there? I'm like literally blinking on every other language that exists. But yeah, other low-level languages, like you might think of like Rust or C++, they're also compiled as well. So optimization of the code happens at this stage. You can set certain flags in your compiler to make sure certain things are optimized. So optimization just means that whatever output is the most like efficiently run code that there can be. So then the question is, well, why give people the option of not optimizing? And sometimes the reason is because if you optimize a bunch of things, if you're trying to debug, a lot of like the code might not show up because like the compiler realized, oh, for certain parameters, like this code won't actually be run. So I'm just going to omit it from the assembly file. And so that can be really hard to debug because you're like, why did I just like jump through 3 lines of code without seeing anything? And you also might not want optimization if you're like trying to control certain parameters. So usually by default, when you're compiling your code, it will just be set to whatever is most optimized, but you can manually set it. And because this is also so difficult, it's also the bottleneck for compilation difficulty. So you might remember from lecture, like they say that, oh, interpreters are easier to write than compilers. And yes, at like a high level, that's true, but at a more detailed level, it's good compilers are a lot easier to write than good interpreters are a lot easier to write than good compilers. And the reason for that is just because, well, the compilers themselves have to figure out like, oh, for this particular hardware that I'm kind of running on, what is the best way to do certain things? And so writing a good compiler will result in really, really optimized code, but it's also really, really hard. Would recommend 164 if you're interested in how that's done. But not for C, because C is a monster, and if you don't, no one's requiring you to compile C from scratch. So the output will have labels. So as expected, in assembly code, we'll see labels, pseudo instructions. So this is really important because pseudo instructions aren't actual parts of the instruction set, which means that if the machine tries to interpret it at this point, it won't necessarily be able to interpret it. It'll also have fully relative addressing, which just means that no like exact memory addresses have been set in memory. And this is really important because you might remember some like instructions being like, oh, these use absolute addressing, these use PC relative addressing, and just means like, how are we like counting the offset from a certain location? So for absolute addressing, the offset is just 0 or starting from 0. What's your offset from that? And right now, like you might imagine, the reason that we can't actually do that is because we don't know where this file is going to go. We don't know what other files are going to be attached to this. So right now, all we can kind of say with certainty is that I know where certain things are offset from my current file, but I have no idea where they are in the grand scheme of things. So then there's a question. If RISC-V is effectively machine code, this is something that's brought up in lecture multiple times. Why does the compilation process not produce exact like machine code as an output? So any thoughts? So the reason being here, because machine code requires for all addresses, labels, and pseudo instructions to be fully resolved. So the assembly file generated here isn't a pure assembly file. So being resolved basically just means instead of seeing letters or like human readable things, I can see now addresses, especially fully absolute addresses, aka I know where everything is in memory. So at this point, like if a human sees like, oh, some label name, they'll know where it is. But if a machine sees whatever label name, they won't be able to identify it. So later on, what will happen is the label name will be resolved into some kind of memory address or offset, just depending on what instruction it is. Does that make sense? Okay. Give you guys 30 seconds to look at this and then we'll move on. Okay. I have no idea if that was 30 seconds or not, but we're going to move on to the simpler assembly part. And also feel free to stop me if there's any questions. Same with online. Feel free to drop in the chat. We have a lovely AI, Sydney, helping monitor chat. So if you have any questions, feel free to direct it there. So I know also we're going pretty quickly because this is like 3 lectures worth of material. But the next part is about the assembler, which does the assembly portion. So what you end up having is the output of the first step, which is an optimized RISC-V assembly file, and the output is going to be an object file. So I'll talk in a second about what an object file actually is in order to get into the next part. But what happens here is, well, most assemblers that we use nowadays are going to be 2-pass assemblers. And what that basically means is you go through the assembly file twice in order to make sure everything that can be replaced is replaced. So this generates, I'll talk about what the passes actually mean in a second because there's kind of a different part to it, but it generates 2 tables to be used later. The first one is the symbol table. So what this symbol table at a very high conceptual level is doing is it's filled with basically a mapping of labels and their relative address to where they're defined. Basically, in other words, we're going to say like, okay, on the first pass of the assembler, we're going to identify, one of the jobs is to identify every single label and maybe they're offset like from the beginning of the file, for example. So how many lines down is it? So they'll go through, okay, label A, we're at offset of like 5 instructions, so 20 bytes. Label 2 is an offset of like 8 instructions from that one, so it's going to be 13 times 4 bytes, and so on and so forth, and it goes through everything. If you try to like look up what a symbol table is and how it's structured, it really, really depends on the assembler. So there's no like universal, these are the different fields that are placed in there, but like conceptually, this is basically what it's doing. So this is also kind of going back to why we need 2 passes to go through things. So for example, if we go through like, say if we have, oh, I should have written example of code. I wonder if I can annotate on here. Let me see if I can do that. I don't. I'm having trouble finding. Oh, wait, no, I found the annotation. Okay. Text. Okay, so if we have something like, for example, code up there. We don't care about that. Branch equal x0, a0, label. And code. We don't care about what code is in there. And then at some point later on, we're going to do label name is equal to, like, say, add I, SP, not SP, let's do A1. No, let's put it in T0, A1, 2. Okay, so if we look at this, what's an issue with this possibly? So imagine like you're an assembler, you're going through and you're like, okay, my goal is to identify where every labeled name that exists is as an offset from the beginning of the file. And my second job is to make sure all the label names are replaced with appropriate like offset from the beginning of the file. If we go through the file once, what's the issue with this code? So imagine if you're reading things from top to bottom, and our goal is to replace label name with whatever appropriate offset it is, and then we keep reading and then we hit where the label is defined. What might be an issue here? A hint is, what kind of errors does Python throw at you if you do something like this? Okay, so yeah, it's a little bit tricky to think about. Someone online said in a DM kind of like maybe it's defined afterwards. And yeah, so the idea is like this can be an issue because our label name is defined after we actually use it. And so this kind of problem is called a forward reference problem or forward referencing, because basically like we use label name and we haven't even defined it at that point. But that's okay, because most of the time we're going to have two pass assemblers, which means that even if we haven't defined it yet, the symbol table will just have a question mark. Like, I don't know where it is, but I do know it's being used. So I'm going to try and replace it on the second time around. So then it keeps going and then it hits label name. It's like, aha, label name, cool, we're in here. And then so then it's able to replace the label, the original label name with whatever offset that it is. So two pass assemblers work great in this instance. But does it make sense why, like, if we only go through it one time, we can't replace the first label name? Okay, let me get rid of the annotations. Okay. There we go. Okay, so now that we have a symbol table, the second table that we have is a relocation table. And so this is for code chunks and for references that need to be, or that we eventually need to say like, need to be relocated. And so what that means is basically, we don't know where these things are. The addresses of these or the values of these need to be computed at a later stage. So the relocation table kind of takes care of, for example, like these symbols that like we don't know where they're referenced from. So like, for example, our previous example, the label name would maybe wind up in the relocation table because we don't know if it's coming from an external reference. So like if it's another file that we have that we're not compiling at the moment, or if it's in the same file, so it's going to go in there. And so once we've established from the symbol table that like, oh, well, in this file, we have label name defined. Then in the relocation table, we can say, this has successfully been relocated, this has successfully been resolved, and we can ignore it now. I also realized like a lot of these words like are starting to get my tongue twisted. So sorry, I'm stumbling a little bit. Okay, so most of the tables, they have other information too. It's just not super important for our needs right now. Okay, before we jump into the next part, are there any questions? Oh, okay. I don't really understand the issue with the code that was just shown. Yeah. I realize I should probably like not have cleared that. Let me see if I can do it. Oh, great. Okay. Now I don't have to retype everything. Let me see if I can maybe like move it over a little. Nope. Okay, so I guess that, oh, maybe select. I think it's select. Select? Yes, there we go. Let's move it to the right a little bit. Okay, so yeah, the issue with the code here is I guess short answer is there's no real issue with the code. The reason I use the word issue is because if we say we go through the code only one time as an assembler, we won't have defined the label name or we won't have defined the label name prior to using it. So if you think of like Java or Python, for example, if you try to use a function before it's defined, like Python yells at you, right? Like 61A problems, 188 problems. Like if you do that, Python's going to yell at you. And the reason is because Python as an interpreter only looks through the code once. It decides not to look at things twice. So it's like, hey, you have to, like, I have an agreement with you as the programmer that I'm going to make sure that you define all of your functions prior to actually using them. And that's just an agreement that you have with the Python interpreter. And similarly here, if you have a one-pass assembler, so aka going through the assembly file only once, that's an agreement that you have with the assembler, the one-pass assembler, that you're going to make sure all labels are defined prior to actually using them. But it's not an issue with a two-pass assembler because then you can go through it once, realize this is not defined, but it's defined later on the second pass. You can replace everything that was a forward reference. Does that answer your question? Okay, cool. Let me clear this again. Hello? Oh. There we go. So yeah, then this is the question. So this is just a review. So are two passes always necessary? And what if there are no forward references in your code? Do we still need two passes from an assembler? So votes yes, no. Or how about okay, I heard this from a different discussion that I was just shadowing for fun from one of my friends, but if you think it's yes, hum, like, and if you think it's no, hum. I'm not sure how well it works, but it's, yeah. Yeah, what are people's just like initial gut reactions? If we don't have any forward references in our code, if we have a two-pass assembler, do we still need two passes? Yes or no? Yeah, exactly. So the short answer is, well, no, we don't technically need two passes, but the assembler doesn't know that, like you said. So we're still going to need two of them because we haven't told the, like, if there were some kind of flag that we're like, oh yes, we have guaranteed that our code doesn't have any forward references, so you can only make one pass, then yeah, it wouldn't need that. But in most assemblers, like two-pass assemblers, I'm going to do two twice just to make sure anyways, because the agreement there is you can have forward references, and I don't trust that you don't, so I'm going to do twice anyways. So yeah. Are there any questions for assemblers? Does anyone want a break? Yes. Okay, we're gonna take a 5-minute break. Take a nap if you need to, go to the bathroom, walk outside. Yeah, it's early. No, it's okay. Okay, so now that we have the assembler, we're going to actually jump to forward a little bit and then come back to the next part, just because understanding how object files kind of look is pretty important to understanding what linkers do. So maybe look at this, like we have 50 slides. We don't actually have really 50 slides. It's mostly for transitions and stuff. But yeah, so the start here on both of these kind of star.o and star.exe files, they just represent basically anything. So it's just like file name.o and file name.exe. But the one on the left is the kind of the file type for object files, and the one on the right is for executables. So you might have seen the exe when you've compiled things. So what goes into an object file? Well, the first thing is an object file header. So what a header actually includes is the size and position of later components. So this is just a file that basically maps, like the header maps where all the later parts are, because it's almost like a table of contents, because we don't know, like we can't, at this point, we can't differentiate between the bits and say, visually, this is where the header, or this is where this section ends, this is where this section ends. So the header tells us exactly like how many bytes or bits offset from the beginning is this particular item. And so the first segment that we have, usually in order, is the text segment. So this is where the machine code itself lives. And this is eventually what gets put into the code or text section of memory. So you can see kind of the names correspond here. So this is like the raw stuff that's going to be quote unquote executed. The next segment is the data segment, and you might be able to guess, but the data segment eventually goes in the data or static portion of memory, and it's a binary representation of all the static data that you have. So this includes like global variables that might have been set, other kind of constants that you might have, etc. And so this all eventually gets kind of ported over to the data segment in one large chunk. And then you have our relocation table. So this is really, really important for the next step, which is the linking stage. And this is because this is telling us everything that hasn't been currently resolved sits in this table. And so the linker has to basically go through everything in the relocation table that hasn't been resolved and say, I have to actually come up with some kind of value that's reasonable. Otherwise, something is wrong. And then we have our symbol table. The symbol table at this point sort of winds up being like almost like a reference or like a key of sorts for other files to use. So I'll explain a little bit how the two work together once we have multiple files going on. And then the last part is we have our debugging information. So you might wonder like, oh, how does GDB actually work? And it's because GDB is kind of paired with GCC, like because it's all in that kind of new system. And so it basically tells us, oh, the compiler is going to have, or sorry, the assembler is going to have a certain amount of debugging information that we can use later to use in GDB, for example. So this is, you don't have to memorize this. This is just kind of like what goes into an object file, and we'll eventually be using each of these portions later on. So we're going to go back to this stage. This other half we'll talk about in a second. So the linker and linking stage, in my opinion, this is probably one of the coolest stages because at this point, up until now, we're only working with one file at a time, like one C file, one assembly file. But the linker stage is when all of these different files kind of come together to become one executable that you eventually run, because it's really unlikely that you'll be running code with just one file because we have a lot of other things that go into it. So what kind of happens here is you have this, it's effectively the quote unquote sum of all the object files that you'll need or want to incorporate, and it's all going to go into some one executable. So if we kind of go back to a few slides ago at the very beginning when we talked about like, if you look at the linking stage, we can see that there are other kind of arrows that go into things. And this is kind of a simplification of it because there can be like infinite number of arrows or n arrows that go into the linking stage, but you can see like it takes in machine code, it takes in libraries that we might have, and it kind of makes it go all together to create that one executable. Okay. So what happens here is, well, one of the first things that a linker does is it categorizes the code chunks, which are called segments, from each object file. So if you remember, we have our text segment and our code segment. Our text segment and our data segments, and we group them together in order. So in other words, basically, if we have files A, B, and C, and we want to put files A, B, and C in order, the linker will decide some order. Maybe it's A, C, B, maybe it's A, C, A, B. And within each of those, it's going to take the text segments, so text A, text B, and text C, and then place them kind of side by side in the order that it's predetermined. So say let's our order is CBA, just to avoid like, oh, it has to be in order in one way. So we're going to have text C, text B, and text A in whatever order that the linker decides. And then we're going to have static C, static B, and static A. And they're kind of all going to sit on top of each other. So now we have two really large chunks of code and then a really large chunk of data. And it's basically a concatenation of everything from each of the separate files. So the linker, if I looked into this a lot when I was kind of writing the call notes, but the linker itself, like it sounds really super complicated, but to write a simple linker, it's really, really easy actually. So if you guys are interested at any point, maybe after like stress is over, it's something really, really cool that you can look into. I was pretty surprised. I thought it was going to be something super complicated, but to write like a generic one, it's not that bad actually, weirdly. So yeah, the order is determined by the linker. So this is also why like we don't have specific notes saying this is exactly how the linker will behave, or this is exactly how things will look. And our standard segments are text and data, like we said. And at this point is when we resolve all references. So how does it do that? It does this in a couple of steps. So the first things first, we remember that we have our relocation table. We also know at this point, well, we've kind of smushed all of the different components into one. And we also know that code kind of goes at the bottom of memory and then data goes on top. And once we know that, then we effectively know everything that we need to know about our existing kind of data. I say data as a whole, like encompassing both of them, in order to resolve the references. Because one of the issues that we had before was we didn't know where the other, say like if we have external references, aka references to things not within your source file, your singular source file. In previous stages, we didn't know where those would sit relative to our current file, but at this point, because we have like CBA of code, CBA of data, we know at the very least what kind of offset that we have in accordance to where we are currently. And so the relocation table is used in this. The offsets that we have from the object file, if you remember, like, oh, this code A is a certain size, code B is a certain size, data C is a certain size. So now we know all that information. So the linker decides, figures out all the arithmetic and kind of jumping out or replacing of information to do this. So the tools that it uses are the object files kind of like header information. It also uses the references from the user files themselves. So if you remember the symbol table, we use them during the assembler stage, and we also use them at this stage because basically we're cross-referencing now. So say if like file A references something from file B, then it'll have to look in file B symbol table to figure out what offset it is from like that current code kind of beginning, because that's what like the symbol table theoretically would store. And then we also know what at this point, like what offset the code, like code B is offset from code A. And so the linker figures out where that is going to be in absolute memory. And then any external libraries that we have, we're going to use static or dynamic linking. So for static linking, which what that means is basically I have all the files locally and I'm going to just literally link them in as if they were another object file. So this is great because it means that it's inherently built into our executable, so it's a lot more efficient. Dynamic linking, on the other hand, is sort of like, okay, every time that we need to use something, we're going to like try to pull it from our library. So it's still going to sit locally. So if you like look into some of the more like quote unquote forbidden areas of like your system, like if you go into terminal and try to like access root and then like look at stuff from there, like you'll see that there's a bin file which has all the binaries for most likely the different libraries that your different systems use, and you might see like a C one in there. And so that's where like a lot of the headers kind of information will go, and dynamic linking basically looks into that and then pulls what information is necessary every time that you need it. So it's not inherently built into the executable, aka it's not as efficient because it's not local. That being said, static linking is not necessarily great for constantly changing or evolving libraries, because that means every time that something small changes in the library, the static library, you have to recompile, go through this entire thing, and then kind of figure it out from there and create executable from there. So go through all of the linking stage again, all of the next stage loading, whereas dynamic linking, because it's like on the fly and pulling it, then you can just start from linker and then keep on going. Okay, it goes through all the relocation entries. We talked a little bit about this earlier. So the result is we have all absolute addresses filled in. So this statement is a little bit iffy, and does anyone have a hunch as to why? So we have like all the offsets calculated and everything, but what's something that we might be missing that we haven't done yet? Do we know where this code is going in memory at this moment in time, based off of information? See a slight shaking of the head. The slight shaking of the head should be a very emphatic shaking of the head, because we don't know where things go yet. But yeah, that intuition is correct. So how the question was, how does the linker know what absolute addresses, like where they actually are, if we haven't specified where in memory to store to? Because up until this point, all we've said is like, we know the offsets, and offsets are great and all, but that's still not absolute. And that's a great question, because we know what we want all the absolute addresses filled in now, but we don't have that kind of vital piece of information. So the kind of answer, I guess, is a little bit of a cheat answer. And so it's something that like came to, there's just basically a standard start of memory location in any kind of program. And it's defined to be, in this class at the very least, and pretty commonly to be 0, 0, 1, and then a bunch of zeros after that when you're looking at it in binary. And so at this point, like, we're still assuming that we only have one process ever run, so there won't be anything there at that point, but we'll be talking about like virtual memory in the last third of the class in a pretty long time, but kind of we'll start getting into that and we'll kind of reference this again. But basically, we're just saying, okay, we have decided that code is going to start from here and everything builds up from there. And so this is just kind of the base location that everything else gets added onto. Ooh. Sorry about that. That was my Slack. But yeah, overall, that is how the linker works. Are there any questions? I know there was a lot of information just thrown at you in this section, but give everyone a few seconds to process things. Feeling kind of okay? Yeah. Okay, yeah, that's pretty reasonable. Yeah, if you're feeling shaky about any of this content, and also like any content that's covered next week, or in discussion, because it's still lagging a little bit for my discussion, there are review sessions coming up, and so we'll talk about this again and go at it from a different angle. So yeah, it takes some time to kind of process. Okay, now we're going to get to the last stage. So the last stage is we're going to have an executable that's going to be loaded into memory. And so before we get into how this works, as with kind of the linker stage, we're going to take a look at what the executable actually holds. So we're going to skip through this part. So the executable header, that's the very first thing that kind of goes on. And you can see that it mirrors the object header quite a lot. So it contains the size of the text and data segments, but you'll notice that it doesn't actually include the position of the later component. And so that's just because at this point, we know where certain things go. So we only need that offset at this point. And we don't need to identify where the specific locations are. So the goal of all of this is include the least amount of information possible while still giving us what we need. Oopsies. So why do we not need the location? I guess I just answered that. And then we also have the text and data segments themselves. So these are actually going to be just all the text and data segments concatenated all together. So like the sum per se. And the format used for both of these is called ELF. So you might see this like occasionally referenced, and what it stands for is executable and linkable format. And it's just the standard format that's used for both of them, because you can see that it's pretty similar across the board. Like we don't have the relocation or symbol table anymore, which makes sense because we don't need them anymore. But everything else like matches up one-to-one pretty well. So it's just one kind of universal format. It's just extra information. You don't need to know that, but. Okay, going back to the loader part. Oops. So this particular segment starts getting into things that like the operating system does. So if you're feeling a little confused about like how exactly does this work, that's okay, because OS stuff we'll cover at like a very high level, many lectures down. But this is you can kind of just assume that the loader and the linker kind of work together, and then the loader works with the operating system to set up everything. So not everything will make like exact sense at this moment. But the first thing that the loader kind of does is it sets up the necessary kind of space in memory for loading all of this information. Because one of the things that we kind of might remember from the memory section of this class is that like the stack and the heap, they kind of grow and shrink as it goes, but the static and data segments don't change in size. And so we also know that the static and code sections have their unique permissions, aka like we shouldn't be able to edit the code as we're like going through. Like sometimes on past exams you'll see like self-modifying code, and it's like you'll see why it's a nightmare, and you don't want that in real life. So in real life, like the code segment is strictly protected, but we don't want like a random amount of memory to be strictly protected. So instead it only protects how much code we actually have, and then loads that into memory. And then similarly for the text data segments, some of it is like writable, some of it's only readable. So we want to make sure that all of that is set up properly. It also initializes the stack to hold the arguments from the program in the reverse order. So like if we do / like execute or whatever, and then we have arg1, arg2, arg3. On the stack, it'll look like arg1, arg2, arg3 from bottom up. And this also kind of sets up where the stack is going to start in memory, because like we've abstracted away so far to say that like the stack starts from the very, very top of memory and the code starts from the very, very bottom of memory. But we could see from the previous slide that the code actually doesn't start from the very bottom. And that's because the operating system kind of stuff sits below that. And similarly, like above at the very, very top of memory, there's like high level things that we won't worry about now, but it's stuff to do with like virtual memory things. And so the system decides, okay, this is a reasonable place for the stack pointer, and then we're going to initialize it there. And then it initializes the registers, so it clears everything. Theoretically, like it doesn't really need to do that, but this is just to set the system up. And then the stack pointer is set to the highest position under the arguments, and any additional setup that is needed to happen. We'll talk more about that in the OS section. And then the stack register, so SP in RISC-V is set to the stack pointer address. So this kind of helps set up everything that is needed to happen later on in order to execute the program. And then we have additional routines. I say that just because the rest of setup gets pretty complicated really quickly, but this is just at a high level, like what goes on. But yeah, are there any questions? So this is like just top to bottom what happens during call. I realize it's also a lot of information, but are there any questions now about anything? Okay, if not, that's also totally okay, because it does take time to process all of this. I am gonna actually I think I remember what's on the worksheet for the call section. It's honestly not that much, like, yeah, it's one whole question's worth of stuff. So I don't know, does everyone like want to go through that question by themselves for a bit and then go back to the other things? Okay, cool. I'm gonna stop sharing my screen here. I'm gonna share my screen from my iPad instead, and hopefully that works. Okay, cool. So let's go through question 2. So I think everyone should be able to see my screen. So yeah, we talked a lot about call here. So let's actually put that into play. So the first question is kind of like, well, what is the stored program concept and what does it enable us to do? And I also realized I didn't actually define what stored program is. So just kind of as an overview, it's just the general idea that everything is eventually bits and can be considered data. So I kind of referenced it when we talked about like, oh, we just have these 2 giant chunks of data that are eventually going to get loaded. And so what can happen here is, well, because things are just like a program is just like data that's stored in memory, they could be potentially messed around with by like other programs by themselves, aka like things can get changed depending on what permissions are set. So there. The user, other programs, or itself, given appropriate permissions. I think overall, like this is maybe not a super novel idea. Like we've been talking about since the beginning of this class that everything is just bits, and I think this just like reinforces that concept. Yeah, question 2, how many passes through the code does the assembler have to make and why? And again, like these are one of these, it's one of those questions that really depends on like what assembler you're using. But for 61C, we're gonna always operate under the idea of a 2-pass assembler unless we specifically specify a 1-pass assembler. And so we're gonna say here in 61, oops, can't write. So in 61C, 2 passes because we use a 2-pass assembler. And the reason here being, well, we want to make sure we resolve all forward references / forward reference to labels. Okay, cool. Are there any questions so far? Okay, next is describe the 6 main parts of the object files outputted by the assembler. So I'm not actually going to write this because I have no space for this, but we talked about all the different sections earlier. So yeah, does anyone want to shout out like in order of which, or I guess maybe not shout because it's too early in the morning for shouting, but just like kind of share what they remember from the object files, like what might be included in that. Got one answer online for a header. Yeah, we have a header. What else? What comes after that? You have one text. Okay. Yeah, so we have header and then text, which the header is the size and position of the later components acting like kind of a guide map. And then we have the text, which is the machine code, the data, which is stuff that will eventually go into static stuff or code, and then the relocation table, which is things that need to be resolved by the linker, the symbol table, which is acting as sort of as a reference or a table, or sorry, a key for the relocation table eventually, and then debugging information. And then so for the last, which step in call resolves relative addressing, and then which step in call resolves absolute addressing. So any thoughts for those two? So for relative addressing, we have our assembler that takes care of that. And the reason for that is because resolving it basically just means like converting from something that's not machine readable to something that is machine readable. And so relative addressing gets resolved by the assembler when we start replacing labels with their appropriate offsets. So with the assembler. When labels are replaced, are replaced by their source file offset. And then so similarly, we have our absolute addressing, and we really harped on this about it during the linker section. So the linker is the one that resolves absolute addressing, and the reason that it's able to do that is because we have all of our files kind of stitched together at that point. So absolute addressing is resolved by the linker. Because at that point we have all necessary files stitched together. So are there any questions for this question overall? Okay, great. Sounds like we have a better understanding of call. I guess we have about half an hour left. I do want to try to end on time today because I have to get to lecture and set up everything. How do we feel about maybe going through an example of like instruction format kind of breakdown or encoding? Or are we feeling okay on that front? Yes to covering it, or yes to being okay with it? Okay, oops. Okay, I'm going to just share my screen. I'll go over it a little bit quickly just because today I think like these are the two main topics. So I do want to cover it in case anyone watching online wants eventually like wants to kind of talk about it, but oh wait, yes, okay. Oh wait, but I'm not screen sharing anymore online, hold on. So we'll go through this kind of quickly and we can hopefully maybe end early if possible. I know the time is a little bit tight. Okay, so yeah, this section we're just going to be talking about kind of like direct translations of instructions. So this was mainly what this, I guess, discussion was technically supposed to be about, beyond call. Yeah, so this is kind of the section that will also, it ties directly into call because this is the part, like we're basically acting as the part of the translation and resolving these different addresses. So we're acting as the part of the assembler in this case. Okay, so kind of going first, this is just the way that I like to approach translating an instruction, especially on exams or when maybe time is tight, because it can be really easy to lose track of things. So the first one is I like to rewrite the instructions without the ABI names. So basically use the register numbers. So instead of saying RA, maybe using X2. I forget all the other mappings promptly right now. But the reason that like this is important is because the value here, like eventually when we talk about RS1, RS2 in the instruction formats, those are basically indexing into an array of registers that's telling us, okay, this is the index that we're looking at, whereas the ABI names don't really tell us that. And then determine the instruction type. So the way that you can do that is by looking at the opcode, because that tells us exactly what family it's in. So all the instruction types have a different opcode. The I-type instruction actually has 3 different opcodes, one for like regular instruction or I-type, so like SLLI, add-I, things like that are very standard. One opcode for, I think it was load instructions, and then one opcode, actually no, there are 4, if I'm not mistaken. So yeah, one for regular, one for load, load word, load byte, etc. And then one for JALR, because that's also an I-type instruction, funnily enough. And then one for the various types of control instructions. So things like eCall, for example. And then to order the instruction components without the required, with the required or expected number of bits. Basically, when you're looking at things like, okay, this component goes here in the instruction or in instruction formatting. I'll go through an example of this in a second. And then write whatever opcode it is that you need, translate the register values to binary and 0 pad if necessary. So basically, you just want 5 bits of worth of register values. Translate any immediates that, if necessary, and 0 pad or sign extend, depending on what's necessary. And then subtract whatever offsets from your PC if you need a PC offset. So this is for things like branch or JAL to a label. And so it's always destination minus the current PC. So sometimes it might be negative if it's higher in the code. Sometimes it might be positive if you're jumping to later in the code. And then you want to encode the offsets as a 2's complement signed representation. So you want to have proper sign extension. Concatenate whatever required bits that you have. So if you have more bits than what you are allotted for that particular component, you need to first chop it off and then stick it all together, and then convert to hex if necessary in 4-bit increments of chunks of 4. So because it's a lot easier to read instructions when they're in hex as opposed to 32 bits. Oops. So yeah, this is just the general kind of way to look about it. If you are going in the reverse direction, it's kind of like breaking it apart first into the required chunks, concatenating the correct number of things, and then translating in the other direction. So, okay, I'm going to, so this is a question actually from a CSM worksheet, because I think it did it really well in terms of how it was set up, but we're just gonna look through some sample code and then kind of deconstruct it. So if we have a loop right here, that's literally just called loop. Side note, if you have a loop label and you want to make sure that you remember it later, I always like to call it like start loop or end loop or whatever, or jump loop or something like that. So we're ending T2, T1, 1, and then we have shift right left logically immediate by some number of things. We don't really care about that. And then we have a branch less than unsigned, which is T1 is being compared to A0 in an unsigned manner. And if it's less than it, then we're going to loop again. Otherwise, if it's greater than or equal to it, we're going to go to the end or go to the next instruction, which is a JALR instruction to the maximum positive immediate. So the first question is, I also realized I'm still in call over here, so I can look on here. I keep forgetting that. But the first question is, what is the value of the byte offset that would be stored in the immediate field of the branch less than unsigned instruction? So instead of having loop, if our assembler were to look at this, what's the offset that we would have instead of loop? So I guess we first think about like, well, where does loop actually jump to? So given our current, like, let's say we have ANDI is instruction 1, the shift right is instruction 2, branch less than is instruction 3. What instruction do we jump to if it's correct or if it's matched? So if T1 is less than A0, do we jump to loop or do we not? Yes, okay, so we jump to instruction 1, right? And so if we were to look at instruction 1 and instruction 3, what kind of instruction offset do we have? So how many instructions difference is it from where we currently are? 8 bytes, right? 8 bytes, 2 instructions, 8 bytes. And because we're jumping backwards, because it's a loop, if our destination is the loop label, and that's 2 instructions back in memory, so it's going to be actually negative 8 bytes. Yeah. And then our next instruction or our next question, does that make sense? Are there any questions? Okay. So the next question is, what's the binary encoding of this instruction? So use hex, and that's where we're going to get into the very interesting part of things. Okay, I'm going to try to get through this in 5-ish minutes, so we have 20 minutes just to buffer and then walk over and do whatever else is needed. So the first step is we want to have a breakdown of our instruction, and here we know that it's a branch instruction, which is going to be broken down like this. So on the exam, you'll have like a green sheet or the reference sheet. So you don't have to like commit to memory all of this, but it's good to be familiar with like what you're looking for. So when we're looking at this, we have our immediate and we have this 12th bit or 12th index bit. And then it's concatenated to bits 10 through 5. And then we have our RS2, RS1, function 3. And then we have another set of immediate bits, which is 4 through 1. And then that's concatenated with the 11th bit. And then we have our opcode. So immediately, like, it looks really funky. It's like, why are all of these in different positions? And it's just because it's logically what's easiest for the hardware to figure out. And when you kind of do the CPU project, you'll see a little bit of why that is, because hardware logic is different from our human logic. So our opcode is 11000011. And our funct3 is 110. These two values will not change no matter what kind of inputs you have. So the immediates, the registers, they'll all change depending on like what you put into that particular instruction. But for branch less than unsigned, it's always going to have this opcode and this funct3. And then so we're going to translate the registers and the different immediate values. So T1 is equivalent to X6. And so in a 5-bit representation, we have 0, 0, 1, 1, 0. We can see we 0 padded by 2 bits to kind of fill in the space, and or 0 extended to fill in the space. And then A0 is X10, so that's 0, 1, 0, 1, 0. So, and then we have our loop, so -8. So we can see that, okay, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait, sorry. Count how many this is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. Okay, so yeah, when we're representing -8, so it's 2's complement. So as a reminder, it's you take the positive 8, get the positive representation, flip all the bits, add 1, and that's your negative representation. And we can see based off of our immediate encoding that we have 13 bits worth of immediate, because our biggest bit index is 12, and we know that we start with 0. So that's 13 bits worth of immediate. Does that make sense so far? Okay, so now that we have this, well, okay, if we do loop T1, so the kind of vertical bars are just concatenation symbols. So if we do loop T1 A0 func3 opcode, is that correct? Instruction is up there for reference, by the way. So yes, no, not sure. So you don't have to substitute in the values just yet, just like, I guess, look at the different tags and see if they seem to be in the correct location. No, why not? Yeah, so exactly. So one of the biggest things is like loop is all together right now. We can tell that the immediate's supposed to be in at least 2 different spaces. Okay, so then now that we have that, is this correct? So we see our immediate's gotten broken up into the way that we expect it to. Is that correct?
I'm not sure about the RS1 and RS2.
Okay, yeah, so that's a really easy kind of mistake to make. And so yeah, these kind of questions are like pointing out the easy mistakes here. So the first one is like, if you forget to break up the immediate, result in issues. So yeah, this one we have T1 and A0, and if we look at the instruction mapping, that would imply T1 is RS2 and A0 is RS1. But this is almost always the case when you're reading an instruction like that. RS1 is to the left of RS2 typically. And then if you have a destination register, it's to the left of all of that. So like reading this left to right, if you did that, then the mapping would be flipped. So in that case, then we have this. So we can see that A0 and T1 got flipped, and so we have some sort of result from here. So is this correct now? Yes. Yeah, looks correct. Yeah, so our kind of breakdown now looks correct. Now we just have to substitute the values in. And I gotta put, okay. So one of the main issues with what we had before, like if we looked at kind of this, is that our loop -8 has 13 bits. And we can see that like we don't actually use the 0th bit when we're doing the immediate. And the reason for that is because, well, when we're jumping for instructions, so with JAL and with branching, we know that in RISC-32 that all instructions are going to be 32 bits, which is 4 bytes. And by jumping in increments of 4 bytes, that means our last 2 bits are always 0. So to save space, we're like, okay, if we know they're always 0, then they don't have to be in the encoding themselves. That being said, then why is only like the 0th bit and not also the first bit gone? And the reason for that is because of legacy code, because in the past, like we had 16-bit instructions, and we want to be able to support that as well. And there's also an extension in RISC-V that allows for compressed instructions, which is also 16 bits. Like you'll notice we have a lot of zeros going on, like if we don't need certain things. And so 16-bit compressed instructions kind of take care of that. So we don't want like a different interpretation every time that we have to like change something like that. So we're just going to say, okay, we'll chop off the 0th bit and then figure out the rest of it. So when we're looking at that, we don't want that kind of representation. Instead, what happens is, well, we're going to chop off the 0th bit. So we can see it's kind of like pale pink now. And then we're going to add another bit on the other side. And the reason for this is now we have the correct number of bits still, but it's encoded in the way that we expect. So now we can have an extra bit to work with. So we have more jump breadth in terms of where we can jump, because we already know that the 0 is going to be there. So once we decode the instruction, we can just add it back in. So now that we have this, that is correct. So what we had before was correct. It was just our immediate itself wasn't correct because we had forgot to drop up the last 0. And that's a mistake I've made like countless times. So this is something I just pay attention to, especially for branch and jump instructions. So now that we kind of have that, we're going to put all the bits back to where we need. So the loop immediate, we want the 12th bit, or so then that's a 1. And then the next series of bits, that's a series of 1s. And then we want a 0, so we're going to sub that in. That's going to give us 0, 1, 0, 1, 0. T1 is going to give us 0, 0, 1, 1, 0. Funct3 is 1, 1, 0. Immediate, we want 4 through 1, so that gives us 1, 1, 0, 0. So towards the very end, and our 11th bit is 1, and then we have our opcode, which is going to be 1, 1, 0, 0, 0, 1, 1. So now that we have that, we now want to group it in terms of hex digits. And so now that we have the binary form of the hex digits, I can convert that to what the actual hex digits are. So that's how we wind up with our final encoding. Good on that? Okay, cool. How do we feel about stopping 17 minutes early? Yes, okay, cool. Yeah, I'll be around for probably around 5 more minutes just to convert things and answer questions. But yeah, if you have any questions, let me know. I'll be heading over to Wheeler in a little bit. But yeah, thanks for joining today at this early time. No, it's okay. Let me. No, honestly, I'm feeling sleepy too, so.